So in today's lesson, we are going to review some things we've learned in the past about functions and their graphs, and potentially expand that into a few new ideas. To begin, let's look at the definition of a function. Right? A function consists of a set of inputs that is called the domain, a rule by which each of these inputs determines one and only one output, and that set of outputs which we call the range. Now, one of the first things that we learned how to do with functions was to even determine, is this thing a function? Based on this relationship, can we tell, are you a function or not? And so looking at graphs, I've given us a couple to compare. And the way that we can test this rule for functions, that it is input, run through a rule with one and only one output, we use the vertical line test on our graphs to determine whether or not the relationship is a function. So you can see what we can do is pass this vertical line throughout our function, and we're looking for points of intersection that are more than one time. If that vertical line hits our graph more than once, then we don't have a function, because that would indicate that the input has more than one output. Notice here for the absolute value graph, that vertical line, no matter where we pass it through, would only hit one time. So yes, this is a function. Even though there are some places on this S-curve that would only hit one time, because there are spots on this graph that have one, have two, have even 3 points of intersection with that vertical line, this is not a function. Now, what if we don't have a graph? What if all we have to work with are a table of values or sets of points? Well, we can still compare this input versus output relationship to figure out whether or not we have a function. Now let's just look at table A, and let's map this. Let's take a look at the domain. It looks like we have 1, 2, and 3 as possible input options. And for the range, or the output options, we've got 5, 6, 7, 8, and 9. If we were to map what's going on here, 1 outputs both 5 and 6. 2 outputs just 7, and 3 outputs both 8 and 9. So because 1 outputs more than one thing, or 3 outputs more than one thing, right, that's a domain repeat. And domain repeats indicate that we don't have a function. Conversely, if we look at table B, and again compare the domain with the range, when we map this, 1, 3, 5, 7, and 9 only have one output. And so because there's no repeat in the domain, this is a function. And you might be wondering, 1, 3, and 9 all output to 5, and that is okay. Range repeats do not disqualify a function. Now, one of the other skills that we learned early on with functions was this idea of evaluating, right? Or finding the value of a function at a certain point. So let's look at the function f of x is equal to the square root of x plus 1. And let's figure out what f of 3 would be. Well, remember, f of 3 basically communicates what's the output for the function named f when the input value is 3. Meaning, let's plug 3 in for x and figure out what y is going to be. Well, if we were to simplify from plugging in, we would find that f of 3 is the square root of 10. But one of the nice things that we have at our disposal with these TI-84 calculators is that, especially for more complicated functions, now this one you really wouldn't need the TI for, but for more complex polynomials, rational functions, radical functions, etc., having the ability to use the technology to evaluate functions is quite nice. If you were to load your function into any one of your y categories on the graph, using the second mode button to quit back to the main page, there's a nice little menu in the alpha trace that's known as the y variable menu. And you'll notice there's 1 through 10, right? All 10 possible inputs for y. Now when I put this function in, I put it into y1, so I'm going to select the y1, and then we're going to open it up like a function notation. y1 of 3 spits back out this 3.16 and change. Now again, these TI-84s will give us approximate values, but we can go ahead and compare what we found to the square root of 10 and notice, okay, yes, these values do in fact match. So when you're going ahead and using the TI to evaluate functions, understand that it's very likely that you're going to come up with an approximate value. So if you're being asked to find exact values, you will not want to use this method for evaluation. And this leads us to a different type of evaluation, one where we evaluate linear or other functions as the input to the greater function. So here we have f of x is equal to x squared minus x minus 2. And notice we're also going to say that h cannot equal 0, because if we were to look at this next piece, this f of x plus h minus f of x all over h, if h were equal to 0, we would have a denominator 0, and we know that that is no good. This statement here, this f of x plus h minus f of x all over h, is known as the difference quotient. And this will have greater applications as we start to move towards calculus. We'll look at how this applies a little bit later on down in this chapter. But for today, it offers us an excellent opportunity to practice higher level function evaluation. We would begin by plugging in x plus h for x in our function, right? That's the f of x plus h piece. And again, that leaves us with x plus h quantity squared minus x plus h minus 2. To then subtract f of x, we simply need to subtract all of the original function. Again, keep those in parentheses because that's one number. Putting that all over h, then we can expand, we can distribute, we can combine our like terms. So how we have 2xh plus h squared minus h all over h. Now again, to simplify this down even more, we could factor h as the GCF out of the numerator, and we could cancel those h's, finding that the difference quotient here is 2x plus h minus 1. Now the simple application of the difference quotient is that it gives the function's average rate of change over a certain interval. So if you define an interval as the amount of space that's gone by and call that interval h, then it will allow you to know for this curve, for this line, for whatever function it is you're working with, what is the average rate of change over that interval. This difference quotient allows you to find that. The last two types of functions we're going to look at are what are called piecewise defined functions. I know that many of us have had some experience with piecewise defined functions, and they are creatively named as they are functions that are comprised of multiple pieces over specified domains. So here, f of x is equal to 2x plus 3 when x is smaller than 4, and it's defined as x squared minus 1 when x is between and equal to 4 or 10. Again, the graph of this would look something like this, where you have the line for all values that are less than 4, and you'd have that small piece of the parabola between 4 and 10. And using these different pieces of information, you can evaluate in the piecewise function, right? If you needed to evaluate something that's smaller than 4, you would use the line. If you needed to evaluate something that was between 4 and 10, you'd use the parabola. And of course, we can see here that the domain for this piecewise function caps at positive 10. So anything beyond positive 10 does not exist on this function. And so this leads us to a specific type of piecewise function known as the greatest integer function. And the greatest integer function, which is noted as f of x is equal to brackets around the x, is a specific piecewise defined function comprised of many different parts that effectively asks us to take a value for x and round it down to the next nearest integer less than or equal to that value for x. So in practice, if we were to find f of negative 4.7, for example, well, if we were to bracket in the negative 4.7, what that's really asking us to do is round down to the next smallest integer. So negative 4.7, of course, is not an integer, and so the next smallest integer would be negative 5, right? So the output, f of negative 4.7, would output negative 5. Notice we're not rounding up ever, we're always rounding down. If you happen to stumble upon something that's already an integer, evaluating the greatest integer of an integer, it's just going to be that integer, okay? So nothing over the top complicated for those. And if you have to evaluate something that is, a constant, right, a specific constant like pi, we can approximate what the value of pi ought to be, right? We know that if we were to round down Since pi is about 3.14, then the greatest integer of pi is 3. And sometimes the greatest integer function graph looks like, or is known as, a step function because it kind of looks like a staircase. For every set of values that we increase by x, once we hit the next integer, we bump up on the range and build the next step. Notice that the endpoints are open, right? And then the starting endpoints are closed. These indicate, again, our included versus our excluded values, such that when you step up to the next spot on the range, that's where the value is included, all the way up until we would step up to the next value. This also can be accessed on our TI-84 through the Math menu. And if you click right to the num subheading, it's down, I think, 3 or 4 spots. It's known as the INT open parentheses. So you can use the INT to evaluate the greatest integer function as well. So my hope is that we've been able to review a handful of these things that we've looked at in functions over the years and potentially explored a couple of nuances to prepare us for our next function unit.